Chapter 6 is about exponential and logarithmic functions, and we are going to start section 6.1 talking about exponential functions. So we hear that word a lot, like these things grow exponentially, but in mathematics this word has a special meaning, and we're going to see what that is. And let's start with an introductory problem. So suppose that you're 20 years old and you inherit from your old uncle $15,000. And you're very wise, and you decide to save that money for when you're going to retire at age 65. So that's 45 years from now. And you invested in the stock market where it grows an average by 9% per year, which is actually not impossible. And the question is, how much money will you have when you retire in 45 years? So let's take a look at that problem. And maybe in a table, we're going to write down how much money we have after t years. So we're going to start when t is 0. So this is initially what you have, $15,000. So in the second column, I'm just going to put down the amount you have for various values of t. And of course, next step is to see how much will you have a year from now. So the way this works is that this is how much you have, and we'll assume that you're making 9% of that during the first year and the second. So in average, you're making 9%. So some years, in reality, you can make more than 9 and less. In some years, less than 9. But let's say an average. Okay, just to make this simple, you make 9% in average. How much money will you have? Well, after 1 year, it's going to be $15,000, and you need to add 9% of that. So it's going to be 9%. Multiplied by your 15,000. Yeah, pretty much like you calculate taxes when you buy something, right? It's 13% tax on something, so it's going to be the amount plus 13% of the thing that you purchase. So overall, we could calculate this, but I want to actually come up with eventually a general formula for the amount. So here I'm going to factor the 15,000, so we'll get 1 plus 9%. Now, what's 9% in decimals? It's this, right? 0.09, like that. So actually, I'm going to put that together, 1.09. Okay? And if I calculate this, I get 16,350. So already after a year, you've made $1,350, right? That's pretty good. So if you don't mind, I'll put my dollar sign at the end like that. Okay, so this is year 1. Okay, let's look at year 2 now. Year 2, you start your year with $16,350 in the bank account, and after a year, you again make 9% of that amount. So doing the same arithmetic, it's going to be 16,350 times 1.09 again. Okay, I could calculate this, but I'm going to actually remember the 16,350 from year 1, it's actually equal to 15,000 times 1.09. So I'm going to write that down. 15,000 times 1.09. Okay, so that's your 16,350. And remember, it's again multiplied by 1.09. So we get that 1.09 is actually squared. So it's 15,000, 1.09 squared. So what is that? We can calculate this now. $17,821.50. So that's year 2. Okay, and again, we can start repeating this for year 3. Okay, year 3, it's going to be the amount you had at the end of year 2 plus 9%. Okay, so of course, this is equal to this times 1.09, but now remember this amount here, which is the same as this is 15,000 times 1.09 squared, and then we multiply that by 1.09 again, so the 1.09 now gets cubed. Okay, now we start to see that there's a pattern emerging from this. So as we calculate this now, we get $19,425.44 approximately. And what's the pattern? Well, you see that if you've got 2 here, you've got a power of 2 here, power 3 here, power of 3 here, and 1 here. Well, you've got a power of 1. Well, I wouldn't write it down. And 0, even 0 actually works, because this is as if it's multiplied by 1.09 to the power of 0. So we get that after t, well, let's say 4 years, just to apply the formula, it would be 15,000 times 1.09 to the 4, okay, which you can calculate. Now that's $21,173.72. Okay, and then we can actually find a formula after t years. Okay, it would be 15,000 times 1.09 to the power of t. Okay, and ultimately we'd like to replace t by 65. Okay, what is that? That's going to be 15,000 times 1.09 to the 65, and then, okay, this is going to be spectacular. Remember, it's just 15,000 we had initially, and 45 years from now, that's going to be 4,0,6,2,6,8,9. I'll even add you the dimes. 4 million something. Isn't that impressive? So just from those $15,000 you've saved, 45 years from now, it's going to be worth 4 million. And this is not, I mean, this is a problem where you inherit from your old uncle. But imagine you work like 2 summers and you make $7,000 each summer, or maybe 3 summers, and then you earn 5,000. You save all that. You got your 15,000, and you wait for 45 years. You're going to be a millionaire. Anyway, so this is the wonders of continuous growth. So overall, we've got A of t, our amount, okay, given by 15,000, 1.09 to the t. So notice how this is different from the functions we've seen before. So in the previous chapter, the variable was in the base, and then often we had, a power of that variable, like t to the 3 or 3t to the 3 or 4t to the 3. So the variable was in the base before. Now it's in the exponent. That's what is making this function different from a power function or a polynomial function, and it's going to be called an exponential function. Is in the exponent. Ultimately, you could have the variable both in the base and in the exponent. That's a different kind of function. So here, the base is constant, the exponent is not. In a power function, the base is the variable and the exponent is constant. So we're going to define our exponential function. So an exponential function is a function of the form f of x equals a times b to the x. So notice how there's no bracket surrounding a and b. That's because only b is affected by the exponent. A is just a multiplicative factor. Now a could be anything. Okay, so where a could be any real number. B is going to be a real number, and b is going to be actually a positive real number. And there are 2 cases that are interesting. The case where b is between 0 and 1, or the case where b is above 1. The case where b is equal to 1 is uninteresting, because if you have a 1 to the x, that's just going to be a. So it would just have a constant function, which is somehow different from an exponential function. So we're going to consider cases where b is, like, you can think of it as a fraction, like a half, that's between 0 and 1, or something that's larger than 1, for example, 2, 3, 4, 5, etc. Some things to note about this. Note number 1, you can replace x by any value. So maybe an example, just to have something in mind, could be 2, 3 to the x. Okay, 3 to the x, you can try it on your calculator. You can replace x by anything. It won't break down. Okay, in fact, okay, the idea is that if you replace it by 2, you're going to get 9. But you can even replace it by a fraction that would be the same as square root of 3. And you can replace it by a negative fraction, right? Remember, that's going to be 1 over 3 to the 1/2, so that's 1 over root 3. Okay, so it's possible to replace x by positive and negative numbers, and even 0. 3 to the 0 would be 1. So the domain is all real numbers. Okay. Now 3 to the 1/2, that's root of 3. 2 to the -1, that's not a negative number, right? That's 1 over 3. 3 to the -2, that's still not a negative number. So these are all positive, right? So what the range of the function is going to be is going to actually depend on what the sign of a is. So if a is positive, the function will have a range that's all positive numbers, because b to the x will always be positive. Okay, so maybe here b to the x is always positive. So the range will depend on the sign of a. Okay, so if a is positive, the range is going to be everything above 0. If a is negative, it's going to be everything below 0. Okay. Third thing to note, which I've mentioned before, so this is different from a power function. Let's say g of x is a x to the n. So here, the variable is in the base, not in the exponent. And not the exponent. So this is how you can tell if you're dealing with an exponential function or not. Typically, there's going to be a variable in the base. Maybe fourth comment, which also I've mentioned, like b to the 0 is always 1, right? So that means that if you calculate f of 0, you're always going to get a times 1. A times b to the 0, so a times 1, which is a. So that means that 0a is going to be your y-intercept. So the a is, which is the multiplicative factor in front of the power of b, that's going to be the y-coordinate of your y-intercept. Okay. So next video for maybe more specific example.